Well, so what have we covered about now? Well, we've basically possibly seen some things you had already learned quite a few years ago. We've refreshed what are we talking when we talk about graphs, what are graphs useful for, and in something a bit more relevant to the problem of processing big graphs, we have seen a few bits in how we can actually represent one of those graphs when we are running our algorithms and how those algorithms look like. What we are going to do now finally is to start thinking in what happens when, again, our graphs become larger and larger and the standard sequential way of solving our problems does not really fit anymore. And that's sadly a common factor for almost every type of graph algorithm. There are very few algorithms that are actually linear in graphs. Even something like Dijkstra, which tends to be very efficient, it does really struggle in the case of Dijkstra when our graph keeps growing. First of all, regarding the time it takes, we definitely need to explore each one of the vertices of our graph. And the problem we have with Dijkstra is that we need to explore each one of those vertices in a very specific order, which is being recomputed whenever we explore the previous steps. That is the worst case scenario you can have for trying to parallelize an algorithm, because if your graph has 1 million nodes, and that's not a too large graph, you know that your algorithm is going to have 1 million steps. And even if each one of those steps is relatively small, you are going to be taking a bit of time until you finally get to the end. It's an algorithm that it will definitely take much longer the bigger the graph is. On top of that, Dijkstra also requires us to have this very useful queue in which we keep all of the vertices of my system with all the distance estimations for all of those vertices, and in each one of the iterations of the algorithm we are updating those distances and we are resorting and repicking what is the top element of that queue. Well, again, if my queue is relatively small, that's fine. As I get to a medium, large, very large size of a graph, just keeping in a single machine and maintaining that data structure, again, it won't work anymore. And because of that, this is one of the many, many problems in which we need to actually find for alternative different ways of solving the same problem, but in a way that can efficiently use more resources. So then, Dijkstra in this case is the most efficient way of solving the problem, but it is the most efficient way of solving the problem if we have one single machine. What we want to look now is for other more stupid approaches but that can use not only one machine but can use as many machines as we need for this actual issue. And well, let's take an example here, and the naive but quite useful way of solving basically the same problem from an origin node, find the shortest distance to every node in the graph. Here, so that we can make it more easier to read, I am saying that all the links have the same distance, so I am counting the number of hops from each node to every node, to one node to every other node of the system. We could solve this with Dijkstra. We can also solve it with one very simple algorithm, which is BFS, or breadth first search, which is basically an algorithm that tells us that we are going to explore brutally all the outgoing connections of my graph, of my initial node, and then all the outgoing connections of each one of those elements. Basically, if we apply BFS, this is much more simple than Dijkstra. We do not need to keep any queue. We basically start with the initial node. It's got a distance of 0. What do we do then? We search in a breadth way. We check all the neighbors, and all the neighbors of the start node have a distance of 1. What can we do next? Well, we pick all the nodes with a distance of 1, and we explore all the neighbors of each one of those nodes. And their distance is going to be, again, the actual distance they have plus the previous. Let's rephrase that. It's going to have the best estimate between the current distance they thought they had and the distance they can get by going through me to the origin. So, to make it a bit easier in a visual way, this is the initial state of my system. And if I am applying breadth first search, I am going to basically be exploring one frontier of nodes at a time. First, I check all the nodes directly connected to the source. Then, all the nodes who are connected to this first barrier. And in this case, finally, the nodes that are 3 hops away from the start. So, in the case of Dijkstra, I would, if I have a total of 4, 8, 10 different nodes, I would have done this in 10 iterations. First one node, then another one, another, and one at a time until I get to the end. The main difference in an approach like BFS is that I can actually schedule this exploration in waves. First all the close ones, then one step after that, then one step after that. And this is not more efficient than Dijkstra actually, because what is going to happen in many cases is that, well, in the case of nodes and edges with equal cost, it's going to be fine. But if I am running this when my edges have different costs, I am going to need to actually do this for all the nodes that I have explored in my system. So first time, I will basically send and check those 3 values. Second time, I will check those 3 plus those 4 that I actually have there. Next time, I will check 3 plus 4 plus the following ones I have here. But what happens if I have resources anyway? What happens if all this graph, this large graph, is anyway partitioned and distributed across many machines? Well, if that is the case, then I am actually finishing in this particular example my algorithm with 3 steps. And in general cases, I will find a solution in BFS in a number of iterations equal to the diameter of my graph. If the longest path with no cycles that I have here is 10, I will get a result in 10 iterations. Whereas in the case of Dijkstra, I need 1 iteration per vertex of my system. And it is actually because of this difference in how we are actually approaching things that this is an algorithm that is much better suited for implementing a parallel exploration of my graph. Because I am not trying to be smart like Dijkstra is. I might be wasting some effort and redoing some of those things by having to recompute it multiple times, but I can do quite a few of those operations in parallel, and I am really compressing the number of iterations that my system takes. And in general, this is the main difference that we are going to be following in either opting for a sequential algorithm for a graph or a parallel algorithm. Parallel algorithms tend to be more stupid, mostly because they want to parallelize the operations into some subset, into some sub-range of the graph. They no longer can check some global data structure. In the case of Dijkstra, we have our global queue that tells us first this node, then this node, then this node. But if we don't have that global structure, we will need to figure out ways to perform some of those tasks in parallel and make sure that the solution is correct at the end, even if we are wasting some time in the middle. Okay, so that is much more close to how we are going to be approaching things if we want to process graphs in parallel. And I am going to focus on this way of solving problems, but I also wanted to mention that this is not the only way in which we can actually approach how we deal with large graphs. There might be, this is what it will happen if we want to apply distributed processing, in which basically we will partition the graph into different fragments and distribute this type of computation across my cluster. That is the Pregel model that we are going to see now. But there are other systems that they kind of have their trade-offs, and I think I should mention them at least now so that you have heard these ones. Some solutions are graph stream algorithms. And in the case of those systems, what they do is basically they take the graph as a sequence of edges. If you remember this way of representing the graph that we mentioned there, and what they do is to feed this stream of edges one at a time to the same box. And there are quite a few algorithms that they are pretty good at keeping some summary of the graph, keeping some important state, keeping some important properties, some sketches, and using them for computing some graph property. With this, you only need to have one single machine, and you will be able to get some computation results without loading your whole graph in memory. But they tend to be very ad hoc, specific for the actual type of computation you want to do, and not really widely used, although there are lots of data mining and database researchers that have been exploring this way of performing algorithms. Other type of approaches, they say, well, if your graph is too large, we need to find either a sample of that graph that is representative enough, and quite a few people have found that doing some appropriate sampling will still give you the same results from some global properties of what your graph looks like. If you want to do something like compute the typical degree that you are going to have, some random sampling should give you comparable results to performing the exact computation, and you won't need to use a cluster for doing the same thing. And then for quite a few systems in which they are not interested in processing the graph, but rather in querying, getting some partial elements of the graph and possibly retrieving those elements plus their connections, rather than computing the global graph as we were seeing before, there are quite a few graph databases that they are specialized in this problem. Titan is one research project that has been relatively popular, although it's not too mature, and I was mentioning Neo4j as another system that is really focused on a single machine storing a graph and allowing you to retrieve those elements and be able to compose some queries. We are not looking at any of those techniques. What we are covering here is how to provide exact computations, potentially complex computations when our graph is very large. And then we have to distribute it, partition it over a network. Okay, then this is a general style that we can use to achieve that. How can we actually find some type of general model or some type of general solution for implementing something like BFS? And unsurprisingly here, I was mentioning before that Google only releases papers when they already have their next system in production that is actually solving the problem much better. And one proof that that's likely to be the case is that 2 years after sharing what they did with MapReduce, and everyone in the world chasing and trying to do every type of algorithm with MapReduce, Google published another paper on Sigmod in 2010 saying, well, you have seen MapReduce, but obviously MapReduce sucks for graph processing. It's extremely inefficient there. So if you want to do large-scale graph processing, and we invented PageRank, so we need to compute PageRank over the whole internet, this is the way that we have found out for that. And it's another distributed system that kind of follows the same type of principles we have seen with MapReduce and with Spark. You have one system, one set of components in a cluster that makes sure that everything works, and you only need to worry on expressing one specific computation that they tell you you can use. And in this case, in the case of Google, they found out this very catchy way of expressing graph algorithms, which is you just need to think like a vertex. You need to basically put yourself in the skin of each one of the elements of your graph. And the elements that you will see as a vertex will be what is your current state, what's the current information you have, and, well, as a vertex you can also see who are your neighbors, what is your degree, what outgoing, incoming edges you have, and possibly who is there at the other side. But that's it. Which incidentally is basically the same information that you would have if you represent your graph as an adjacency list. So that is why this is a quite natural way of representing how a graph structure in a way that is very convenient for processing. So then, this is what think like a vertex is about. You can define some computation, whatever you want to do, but the main restriction is that whichever function you define only can have access to that. It's going to be parallelized, so we are going to run the same function in each vertex of your graph, but each one of your vertices can only access the direct local close information about itself and its neighbors. And what can you do with that? Well, basically what you can do is the same idea that I also mentioned before of this bulk synchronous parallel model. We are going to define a computation loop. We are going to define the function that in this case each one of my vertices can do, and as part of my computation cycle I am going to allow each one of my vertices to send messages, to transfer, communicate some information only to my neighbors, because those are the only elements that I can see as a vertex. So then I will have a set of iterations, and in each one of those iterations each one of my vertices can actually send, communicate and transfer any type of information to the neighbors. And when the next step, the next iteration of my computation starts, those messages will have arrived the destination. So then, if we want to visualize then how this computation model works, this is me. I am one of the billion vertices that are resting in whichever, in the web graph, in the Facebook graph. How does a computation cycle look like? Well, when I start this round, the first thing that happens is that my neighbors will have sent me some messages. Possibly some, if this is PageRank, in PageRank we were mentioning that each one of the vertices shares part of their PageRank scores with their neighbors, because it's basically an algorithm that diffuses all those ranking scores across the outgoing edges of each vertex. So maybe if this is PageRank, I am receiving the contributions from the other web pages that have links to me. Well, once I got all those messages, I can use them to recompute. In this case, I can use that to compute my new PageRank score after that, which is a function of my previous score plus the contributions from my neighbors. And once I have finished my computation, I will again spread, share my baseline score back again to my neighbors. With this, I finish one loop of my computation, and once all those messages have been sent, I start again the same process. The same vertex will receive messages from my neighbors in a new round, process them, send the updated results to everyone else. And just by implementing this execution loop with those three parts, how do I receive messages, update my local state and send the messages, it is actually possible to implement every graph algorithm that depends on a lot of graph traversal. So if you need to explore a graph in parallel and you are not sure how to do it, this is a relatively natural model of expressing your computations. And of course, well, this is something that it's going to happen in parallel. My graph will be partitioned over a set of nodes, and each one of my nodes, each one of my workers, will run all those computes and tasks and wait to receive the messages from the other partitions. And after that, start again and again. This has actually been a very, very influential model again, because nobody else has really figured out a better way of expressing parallel computations of a graph. There have been some small tweaks, some small variations, but there has been a family of different frameworks that have been taking this into practice. Apache Giraffe was well, technically still is an Apache project that they did the same that Hadoop did. They took Google's paper and implemented it as it was. Unfortunately, it's a system that it's used by Facebook, but the problem is that it is only used by Facebook. If you download the project from the Apache repository, you can see that it's extremely not polished, it is difficult to set up, it is very much bare bones, so it didn't get any support from the wider community because of that. Spark is the cool tool in the big data framework, and they were relatively quick to also propose their own library, their own GraphX system that I will mention in a bit. And GraphX is a bit unstable, I have to say. We will see this afternoon in the ITL how well it works, but it's still got some quirks and some parts that are not really working as they should, because it's a project that has grown really fast. But these days is really the most popular general purpose graph processing system that is being used when you need to process large graphs. I should also comment GraphLab, that it appeared a few years before as GraphX, but it's also another independent project that provides a similar computing model to this Pregel idea. So that's really how almost everyone has worked and has tried to solve the problem of expressing our parallel computation in some big data way. Rather than defining map functions or reduce functions that we actually could, we could have adjacency lists as RDDs in the case of Spark, and if we are careful in how we use Spark transformations, we could actually implement graph algorithms ourselves. But this think like a vertex idea, it kind of provides us a higher level interface. We know we will have as many cycles as we need, and we have this message send and receive mechanism to make sure that everything is actually communicating nicely. And if we go back now and we see, for instance, what happens here in this BFS implementation, and we think like a vertex, you can see that if this is implemented in something like Pregel, first the source node can start the process and send messages to its neighbors saying, you can get to me with a cost of 1. And then in the next iteration, when every node processes, my neighbors say, oh, I can get with a cost of 1. I like that. I update my value, and then when those 3 nodes are thinking, they will say, you know what, you, and you can actually get with a cost of 2. So they can send 1 message to each of them with this new suggestion. Next iteration, those nodes update. Final iteration, those nodes are actually here. And this representation is actually useful because it allows you to see one main limitation of all those Pregel-style models. We are running iterative computations, and in each one of my computations, I can only travel 1 hop in my network. Eventually, with what's originated here, it did get to those nodes that you see here, but it took 3 steps of this process. And the same thing is going to happen for any Pregel-style computation. Information won't propagate fully on the graph until enough number of iterations have actually gone through. But we can, in theory, do that in parallel for all the nodes. So that is why when our graph is very large, this is actually a very sensible way of thinking of this. Okay, so any question about this idea and this think like a vertex abstraction? This is really the, let's say, the main intuition, the main insight. Now we are going to see what has GraphX done of this, which is a relatively straightforward implementation of that, but this is really the style of computation that you will have to use if you want to express a graph algorithm in parallel. And if what you want to do, again, is some type of process in which you want to process every vertex of the graph at the same time, and you want to communicate with your neighbors, which means that you are searching for something possibly, then this can be a good fit. If you want to do something different, for instance, you want to do something like graph matching, you want to find a set of patterns inside a graph, you can implement it with this type of approach, but it is not too intuitive. And actually, last year, for instance, there was a different paper published, one system called Arabesque, that it was actually proposing another different abstraction. They don't call it think like a vertex, they call it think like, I don't remember the word they use, a strange word, so that you can basically define a pattern, and they try to do something similar to that. They take that pattern and automatically parallelize how you are exploring that pattern in the network. So again, whenever you are working in some type of graph system, make sure to understand what is the type of processing you want to use before you jump, or, oh, I just have graphs, this is a big graph tool, it has to be good for me. Well, those tools will be very useful when A, your graphs are very large, so that you need to distribute them, and B, what you want to do in your graph is basically perform computation across all the vertices. If you are, for instance, running local searches, local queries, just use a graph database. There are lots of systems that will do that in a much more straightforward way than what you can get here with GraphX or one of those platforms. Anyway, let's introduce GraphX, and well, this is one of the few different libraries that Spark comes bundled with in order to provide higher level functionality. And in this case, it basically provides to us one special RDD that captures all the information inside a graph, what they call the property graph. And in addition to the RDD, it also comes with a set of customized transformations that simplify completing many of the common analysis tasks that we want to do of graphs. There are some predefined methods, and there is also an interface for computing something like this Pregel style of computations that we have seen before. So if we already have some basic understanding of how Spark works, and we get the idea behind this thing like a vertex model, this is going to be basically the combination of both things. So then, what is this graph X main element, main RDD that we are going to be managing? Well, what graph X defines is what it is known as a property graph. And as a property graph, we are going to be storing basically three types of information. First, we are going to be storing the structure of the graph. What are the edges, the nodes of the graph? What are the actual edges of the graph? And one note in the case of graph X is that whenever we create a graph with it, all the graphs here are directed graphs. That means that if I have an edge from 5 to 7, that does not mean that I can go from 7 to 5. If that is the case, I would need to have two edges, 7 to 5 and then 5 to 7, so that this is actually a bidirectional connection. Another strange thing of graph X, I will just mention it in case it happens to you, is that this structure is actually not exactly a graph but a hypergraph, which means that you can add more than one edge with the same pair of source destination. You could have in graph X 5 different edges between 5 and 7, and that is used sometimes in some domains, but for the majority of graphs we do not allow that. We only allow one edge per pair of elements. But if you are basically loading a set of elements in graph X and they are creating a graph, keep in mind that any repeated edge will actually be accepted with no problem, because that's what hypergraphs are about. So this is the structure, and in addition to that structure, a property graph can hold properties, which basically means that we can have attributes, some state associated to each one of my vertices, and also I can have some state, some attributes associated to the edges of my graph, similarly to what we can do with a graph database actually. And in this example, again from the GraphX communication, well, we have a graph in which we have nodes represent users of a research lab. Each one of the users, each one of the nodes has an ID, and this is another restriction of GraphX. Whenever we have a vertex, a vertice, we need to have a long number that is identifying uniquely that vertex when compared to all the other ones in the system. So that's something that will be a headache whenever we want to use GraphX and create a graph. We need to make sure we have all those unique identifiers. But then we also can have a set of properties. So the node 3 has two properties. One is the name, Arxin, which is the first author for the GraphX paper. He's a student. He's got a property of being a student. Similarly for edges, edges have source ID and destination ID. Again, they are directed, so they are distinctively source and destination, and they can have one or more properties. Here in this graph, those properties are strings that provide additional metadata, additional information, but we can of course also have some of those properties that are numeric properties. And by having numeric properties, we will be able to compute some actual properties to perform some actual algorithms on the graph and not only run queries. But this is the main element that we are going to have. And again, in this element, each one of our graphs is basically going to have two families, two RDDs of values. The vertex RDD holds the properties and the IDs for each one of the vertices of the system, and the edge RDD is going to hold all the actual properties of each one of the connections that I have here. And in some of the actual methods, in some of the actual elements, GraphX also defines this idea of a triplet, which is basically the joining of source vertex, edge, and destination vertex, so that we can simultaneously access to all of those properties. Keep in mind here that those both vertex RDD and edge RDD, they are again Spark lists, Spark elements, and the only information we have here is the one that is actually explicitly mentioned here. So if I load a graph object, you will see it this afternoon, and I obtain the vertices of that graph, I will have a list, but the only thing that list is going to have is, for ID 7, I will have the property whichever name I have actually defined for that specific edge. For node 3, whichever property I put. Node 2, node 10, but I will have no information basically about the node structure if I retrieve the vertices of a graph. I can compute this in some way, but if I want to actually do something with the structure of a graph, do some type of computation, I will have to use some specialized methods for that, and that's what we are going to see in the final part. How can we create one of those elements? There are a few different modes. The most straightforward is to just read from our distributed file system. If we have a list of edges, source ID, destination ID, source ID, destination ID, and so on, we can give that URL to GraphX and we will obtain a graph object from it. The annoying part of that is that that is going to have purely the raw structure, only 5 to 3, 3 to 7, 5 to 7, 2 to 5. If I have any additional metadata of my graph, I will need to add that afterwards. And there are a few methods that actually allow us to take that bare bones structure and then join it, enrich it with some additional sources. And again, in this afternoon's lab, there is the first part of the actual lab sheet that you will need to complete. How to take my bare bones structure and how to then load additional properties, in which we, for instance, have the name, the actual string name of each one of the nodes that we are loading in the system. Because, to give some context, if yesterday you were looking at a collection of popularity figures for each one of the channels in that system over time, the additional data set that we have today for the lab is a graph figuring out which individual users are following each one of the channels in the same system. So user Felix follows channel X. User Felix also follows channel Y. User Peter follows channel X. And if you want to load that as a graph in GraphX, you actually need to split that into two different files. One will have the identifiers of each one of those nodes. It cannot be user Felix, it needs to be user 1567, and it cannot be user channel X, it cannot be node channel X, it needs to be node 325. And another file is going to actually keep this mapping of user 3257 actually has the name Felix. That's why you will actually see that loading information can be actually not as easier or as straightforward as we would like. The good thing of GraphX is that it is a pretty much a feature-rich library. Once we have loaded a graph, there are lots of methods that we can actually invoke in which we actually can get access to lots of useful ways and actually derive properties from the graph. We can get the list of vertices, the list of edges, and do something with them. We can also get something like the degree distribution of a graph. And then, if we want to observe and we want to do some initial analysis, for instance, in how interconnected are the different elements of our structure, the degrees method is going to return already for each one of the vertices of my system what is the degree that we actually have there. And if we then find out the maximum of this list, for instance, we will actually pinpoint who is the best connected user from my network, without having to go to Pregel and to implement any type of more tricky computation. There are also quite a few predefined classic graph algorithms that are implemented on GraphX. Connected components is one example, and what connected components does is taking a graph, it basically finds what are the actual different connected subgraphs that we actually have there, because it can be the case in some scenarios that our graph is in reality a set of multiple subgraphs that they are not connected with each other. And connected components will already perform that computation and return the list of graphs that actually are present in our dataset. We can also implement something like PageRank. The metric I was mentioning before is already predefined here. So you don't necessarily need to use the more powerful programming interface if you actually want to get access to that. But of course, if you want to obtain either the vertices object or the edges object, you can basically use all the standard Spark transformations and actions that we have seen yesterday, and you can, by doing that, manipulate it and basically querying some aspects of the graph, looking for some specific property, looking for some specific edge, counting how many elements match some property. So all the standard RDD transformations that you saw yesterday can also be applied here if you want to do some general exploration of the properties of the graph. Although you cannot really do much here, because if you get the vertices or the edges, you are basically only getting this information you have here. You are going to need something else if you want to implement some computation with it. So how can we then do something more interesting with GraphX? Well, in order to define our own functions, in order to define our own computations, GraphX provides some more expressive transformations that we can actually define. And the kind of first step simple transformation is called Aggregate Messages, and it's basically the equivalent of one iteration of this Pregel idea. It allows us to send a message through each one of the links, through each one of the vertices of our graph, and then combine, merge all those messages into one single result per node of my graph. So then, if I have a graph, I can define two functions. One function to specify which messages I am sending to my neighbors, and one second function to specify how to combine all those messages together. And if I put those two things together, I can do something like this. I have here one graph in which each node represents a user, and each node has a property that represents the age of that user, and I have a query that is what is the age of the oldest follower of its node. So here, node A, I see that B and C are actually following A. B has an age of 23, C has an age of 42. F is only followed by A that has an age of 30. D is only followed by F, which has an age of 16. How can I compute for each one of those nodes in parallel what is basically the maximum age, the maximum value of that property from all the nodes that are my followers? And this type of computation is actually quite natural for that. We need to define again two functions. First, we need to specify what messages and when we are sending messages. For each edge of my system, I am going to send a message to my destination with the attribute of the source of this edge. What this means is that if I am processing what happens here with this vertex from B to A, I am going to be sending a message to the destination. Those will be executed in parallel, and in this case then we are going to have, for A value is 42, for B the value is 19, for C the value is 23, for let's see, D, E, F, for D we have 16, for E we also have 16, and for F we have 30. And again, this result that we are getting here, this is a transformation, so this is another RDD that we can actually use for part of our computation. If rather than wanting to perform this computation, we wanted to manually obtain the in degree of each one of the vertices of my system, I could also do that. So if I want to obtain what is the in degree, what I would need to do in this case is to basically change those two functions. And if I can see something here which is not that easy, so let's suppose that then rather than computing the maximum, I simply want to get the in degree. So the in degree would be, if I put the graph, for this node it only has one incoming link. This is an outgoing one, so the in degree is going to be 1. For A, it's got 2 incoming links, so the in degree is going to be 2. Well, if I want to compute that, I only need to express what do I need to send, and in this case what I would need to send to the destination, it would be a value of 1, because I am sending one message through it. And here, in order to merge the messages, rather than computing the maximum of A plus A and B, what I would need to do is to add all those elements. Add all the messages, all those 1 values, in order to actually count, basically, how many messages I have received from my neighbors. So, depending on the type of operation that we want to do, this can be useful for aggregating and computing still only local information, because we can only go 1 hop away. Okay? Well, then, if we get how this works, we are almost there to actually see how to implement this thing like a vertex idea that I had mentioned before. And again, the idea of the Pregel programming model is that we are going to express what each one of my vertices does in each one of my iterations, and in each one of my iterations I receive messages, perform computation, and send messages to my neighbors. Well then, what I'm going to do here is again having 3 functions that tell me how do I process the messages I receive from my neighbors, how do I run my algorithm once I have done that, and then what messages do I send to my neighbors. And here, rather than having only this merge message and this send message, we basically have one additional step here, this vproc that is going to basically process how does the vertex state be updated depending on the incoming message that has actually come to it. So let's then pick that again, this model that we saw before. First, we receive all the messages from my neighbors, and what I'm going to do is I'm going to run this merge message in order to actually consolidate them into a single message. Once I have one single message, I am going to execute my vertex program. And for that vertex program, I will reason with the one merge message that I have received. And after I have completed my vertex program, I will decide what messages I am sending to my neighbors. So if I have those 3 steps of my computation, I can use this for implementing something like the BFS breadth first search that I was mentioning before. And what I would have is something like this. Again, I keep having 3 functions: merge message, do processing of the vertex, send those messages. What I'm going to do with those elements? First, we start one iteration, and when I have this iteration, I know that each one of my in degree edges, each one of my inbound connections might have some messages for me. Some message A, some message B, some message C. If you remember how BFS looks like, what those messages are telling you is you can actually get to the origin with a cost of 2 or 5 or 1, whichever number. So this node is telling me you can get to the origin with a cost of 4, maybe with a cost of 3, maybe with a cost of 5. And what I need to do first is to consolidate all of those messages into a single one, which will be the one that matters. If those are suggestions of how far the source vertex is when you go through each of them, what I will need to do then is to pick the smallest of those. I'm going to pick the minimum value of all the different messages that are coming to me. If the suggestions are 1, 5, and 6, I will pick 1 as my new destination, as the actual, my new distance, the suggestion that all my neighbors have figured out for me. Now that I have one consolidated suggestion, this new distance, I am going to execute my own code. And my own code is, okay, this is who I am, this is what I know up to now, this is my current distance estimation, and this is the new suggestion that my neighbors have found for me. Well, what I'm going to do then is to pick which one is best. Is it best to keep my current estimation, or should I take the new distance estimation that is smaller than what I already knew? If the new distance is smaller than what I have, I will update that value. Otherwise, I will keep my initial estimation. What is left for me to do? Well, what is left for me to do is to then communicate any changes to my neighbors so that they can keep re-updating their own internal state on how far they are from the source. And in order to do that, what I can do is to basically figure out which ones of those are going to benefit actually if I send them this suggestion. And then I can go edge by edge. This triplet element here allows me to get access to all the fields in this edge. And if my own estimation plus the cost of going through this link is smaller than what my neighbor thinks is the best option, then I know a better path for them. And then I will actually send them a message with my suggestion. If I cannot find, if I don't know of a better way of solving this, then I will not send a message. So in this type of algorithm, at least I can tweak and I can send messages only when that is going to actually improve the estimation of my neighbors. It's going to move the system closer to completing. And that's the end of one cycle. Once this cycle finishes, each one of the vertices will receive all those messages. Merge will be invoked so that we pick only one message per node. The node will rerun again this computation of its current estimation, and if there was some change, it will again recommend the other node so that they can get to the origin, so they can get through a better path to the origin. Okay? That is now this thing like a vertex idea that we were mentioning before in one specific example with one algorithm. And if we go back to, again, if we go back to this BFS plot, that is basically what it could be happening in one place like here. Suppose now that, for instance, you are in this node in this node 2 that we have here, and this thing like a vertex process starts. The first thing that happens is that my neighbors might have sent some messages to me. Maybe this node said, hey, 2, you can get to the origin with a cost of infinite. We would not send this message, but this node might have sent a message here. You can get to the source with a cost of 1 + 1, 2. First thing is to merge all those different messages into a single one. Best estimation here, it would be 2. Once one single message comes here, we compute the vertex program. Is 2 better than my current estimation, which is 2? Not really, it's the same. So we keep that as it was. Final step, send messages. This node checks each one of the outgoing edges, and for each of them they say, okay, this node has an estimation of 2, and I can get there with 2 + 1, 3. Okay, then it's not worth sending them a message because they already know a better path. This node has an estimation of infinite, and they can get to the origin by 2 + 1, 3. So there would be, they can actually find a better solution here. So then this node can send a message to them so that in the next iteration of this system, when this node merges the messages and invokes the vertex program, it can update it so that it can be actually to the new value. And that's in a nutshell how this thing like a vertex model works. It works very well for this type of search. It is very natural for algorithms like a PageRank. There are some clustering techniques that can also be expressed quite efficiently here because they do, again, they are based off starting on each one of the vertices and expanding to other neighbors and finding some candidate communities, some candidate elements that could be merged from those. And it can be a bit challenging at the start to figure out new algorithms that can be expressed in this way, but over the last years there have been actually lots of research and lots of solutions that do map nicely to this problem. So if the type of graph computation that you need to do requires exploring the whole graph and it requires to be exploring the neighbors in some way, those computations should be able to be expressed efficiently using this model. Okay, and here you can see technically the full source code, which is basically the same of what we have here in the P figure, so I will just leave it for completeness sake, but that's basically all the common main basic intuitions that you need to know in order to use a distributed graph system like GraphX or any other Pregel-based system. Of course, this is just the developer side. That is going to be the angle of someone who is interested in using this platform. There is lots of complexity in what is happening behind the scenes, how to be able to efficiently partition this graph so that all those operations can be executed in parallel at the same time and we don't spend time waiting. How do we minimize all those messages that are taking place so that we don't spend most of the time just sending data across the network. But for the purposes of everyone who is interested in using those systems and not researching of them, I hope that those are enough initial hints so that you could see how that can potentially apply to your research. This afternoon, have fun, enjoy the whatever you can get with the lab, and well, I'll see you tomorrow at 12, and what I'm going to do to grab this week is to, in addition to asking for any suggestions, feedback of what we've done these days, I will try to very quickly introduce what research are people like me doing in this actual field, and to learn a bit more of what are the actual challenges and the actual bits that need to be solved so that users can actually employ this type of frameworks without knowing really about all the parallel complexity that is behind. Okay? Well, thanks for your time, and see you then tomorrow.